email from Joshua a couple of months ago going, do you want to come up to Liverpool? And I was like, yeah, all right, go on. I'm a Microsoft MVP. I run a .NET user group that's under the .NET Foundation. And just listening, it's always interesting listening to Joshua and we do this and we do the YouTube. And I'm like, oh yeah, I need to do that. I need to do that. I should sort that out. That's on my list. So it's kind of nice to be this person instead of that person for a change. The thing that I'm probably best known for around the world is a joke that I did in a bar in Australia in 2018 when I saw a tweet about someone should make a programming language called Rockstar so we can all be rockstar programmers. And I did. And I made a programming language based on the lyrics to heavy metal songs. And the joke got way out of hand. And now the joke is, so that's at codewithrockstar.com if you want to check that out. And yes, it is, you can write songs that look like heavy metal song lyrics and bad power ballads. I am the project manager of the joke. The joke is on version 2. The joke has a test suite. The joke runs on WebAssembly now, thanks to .NET 9. So yeah, commitment to the bit. But that's not the story that I am here to tell you tonight. I'm here to talk to you about plain text. And this is one of those talks that I absolutely love because it has evolved. It's kind of taken on a life of its own. Because I came up with the kind of first draft of it about 5 years ago, and I did it at a couple of online meetups. And then people started sending me like little details and stories and things that I wasn't aware of. And then I started, when the world opened up again, I went out, I did it at a couple of conferences, and some of those put it on YouTube. And people on YouTube have opinions about things, and they are not afraid to share them. And so as versions of this talk have been on there over the years, I've had little comments like this one from Braden going, of course there's such a thing as plain text. Yes, Braden posted an 850-word comment about how there is totally such a thing as plain text and ends up going on something about Arnold Schwarzenegger going back in time to kill your parents. Fortunately, not all of the people on YouTube are like Braden. Some of them are very constructive and helpful. And so there are little bits and pieces that will get kind of woven into the story here, which have come from there. But yeah, plain text. Like, who would go to a talk about plain text? Because the reason why technology is useful, the reason that I like computers and the internet and websites and all that kind of stuff is because the stuff which actually happens inside the technology, nobody cares about that because we don't know where it came from, we don't know where it's going. It's important when somebody can have an idea or somebody can have a piece of music or a piece of art or a piece of writing or a diagram or a code snippet or something, and they can put that into some sort of computer or network or retrieval system. That does something with it. And for me, the value, the meaning is when it comes back out the other end and another person can share that idea. They can run that code. They can see that picture or hear that piece of music or read that message or all that kind of thing. And so an awful lot of the utility, the value of modern technology is about being able to take the things in the real world which are meaningful to humans and turn them into digital information, do something with them and get them back out at the other end. Now, the very first attempt to do this that I could come across was this thing. This is a Cook and Wheatstone 5-needle telegraph system dating from around about 1834. And this is, I believe, the first system ever that took text that human beings can read and turned it into some sort of binary information, or, well, turned it into some sort of electronic information, because we haven't got to binary yet, and then turned it back at the other end so you could read it. Now, it's a really interesting project for a couple of reasons. One, Cook and Wheatstone were the people who collaborated on it. And Cook was a businessman and Wheatstone was a scientist. And Cook said, we must sell this for an awful lot of money and it must be really easy to use so it doesn't need a manual. And Wheatstone said, no, we must give this away for free, but people should have to learn how to use it because technology is complicated, which is horribly prescient because 200 years later, we still have startups where the business person is going, this must be easy to use and really expensive. And the engineers are going, no, we'll make it free, but they've got to read the manual, otherwise they're not going to know how to use it. Now, the way the Cook and Wheatstone system worked is it took 5 wires. They ran 5 wires from Paddington Station to West Drayton, which is a distance of about 10, 12 miles. And this is like before, like telephones don't exist yet. Telegraph, SMS, none of this stuff exists yet. Like it's not like you can phone them and go, hey, switch the machine on, we're going to send you a telegram. We're not there yet. We're not at that point. They've got these 5 wires. And they can be used to close a circuit. So what you do is now the compromise they made. If you wanted to transmit with the machine, you had to read the manual. But to receive, all you needed to do was watch the needles across the middle, because when they closed a circuit, that would create a little electric current, and the needles would move, and you would read off the letter where they crossed over. That was it. It couldn't encode the entire alphabet, but it could do enough that it could send messages about what was happening on that piece of railway line. And it made headlines in 1935. A murderer escaped from the police and got on a train at Paddington to try and get out of London, and they telegraphed ahead and said, apprehend murder man in coat, or I don't know what the message was. But the police got the message, and they came in and they arrested it, and that made the news headlines, and everyone went, telegrams, that's quite a neat system, isn't it? Now, anytime that you are battling against 8-bit and 16-bit binary encoding, just take a moment to reflect. If this had caught on, we would all be using a 5-bit binary encoding system, because every one of those 5 data points could be positive, negative, or 0, and that's how we encoded the alphabet with it, because when they deviate, if it's positive, it goes one way, if it's negative, it goes back the other way. This is not the system that caught on. The system that caught on, a system that a lot of people think was the first real binary encoding system. Now, you'll recognize this, right? It's Morse code. The funny thing about this was not the Morse code that was invented by Samuel Morse. Because the problem with the Cook and Wheatstone system is it needed 5 wires. And then one of the wires broke. And so they're like, well, we can buy another, like, 10, 15 miles of wire and run it all the way through West London. Or maybe we could do it with 4 wires. Or 3 wires, or 2 wires. Meanwhile, over in the United States, a guy called Samuel Morse is like, what if we just had 1 wire? Now, if you know anything about electrical engineering, you're like, you can't do anything with 1 wire. But what Morse did was he realized if you put enough current down it, you can detect the difference between that wire and the ground. So you can actually send a signal using just 1 cable, and you could send enough signal to make something go beep. And so he came up with a system. Now, this is International Morse code, which is named after him, but it's not the actual system he invented. Created by a guy called Friedrich Wilhelm Gerke, who was a German engineer in about 1865. And this is the one that became the international standard. Now, it looks like a binary code. It looks like dot dash, but what you don't see written down like this is the gaps, because Morse code is a time-based coding system. You need to leave gaps between the dots and the dashes, so you know that was a letter, that was a word, that was a full phrase, that's a letter, that's a word. It survived for 100 years. There was a thing in 1865, they had a big conference on international telecommunications in Paris and decided this was going to be the standard. And like any piece of technology, when no one's using your stuff, you can change it as often as you like. As soon as you have paying customers, you can't change anything ever again. That's why we all have legacy systems. And within a couple of years, within a couple of decades, the telegraph networks that supported it had been rolled out all over the world. People are laying cable across the bottom of the ocean. They're doing astonishing things with communication and automation and infrastructure. And so we're kind of stuck with this because no one has a good reason to move away from it. For almost exactly 100 years, because 100 years later, 1965, the Americans come along and they invented ASCII. Now, the American Standard Code for Information Interchange. When we talk about plain text, most of us think ASCII, because what we really mean is, look, I don't want to download an app and I don't want to have to think. I just want to double click and it opens in VS Code or Notepad or whatever I use and I can just read it. That's what plain text is. It's effortless, readable text files. And what the Americans did, now they created ASCII in an age when computers looked like this. Most of them didn't have screens yet. And the ones that did, the screens couldn't show text. For text output, they used teleprinters, mechanical teleprinters, and they would read code from punch tape and punch cards. And so the designers of ASCII, they actually did a pretty good job because they set out to solve a specific set of problems. How do we encode text and the control sequences that are necessary for the teletypes that are being used in the English-speaking North America, United States, and Canada in about 1965? That's the problem. And they sat down, they figured it out, they did a frequency analysis, they worked out what needed to be in, what needed to be out. They came up with this. Now, if we do a little tour of the ASCII, the basic ASCII character set, we start off with, we've got ASCII 0 there, the null character right at the top of the stack. And any of you folks who's worked with C or C++, we still have that today because C decided that's the end of a string there, because if there's no more noise coming down the electrical teletype, you've probably reached the end of the message. Hey, that works, we'll use that. Then there's this bunch of control characters. If you wanted to print the start of a heading on your teletype machine, you would hold the control key and you'd press A. And if you wanted to send the start of text, you'd hold the control key and you'd press B. And if your teleprinter is going brr, 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 and you're like, no, 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 stop, there's been a horrible mistake, you press Control and C, which is how you get it to stop sending text. And that was kind of survived, because we do that when we write infinite loops. We're like, no, stop, Control C. And so we're using this relic of the 1960s to stop a .NET program with an infinite loop in it. And then we've got a whole bunch, end of transmission, inquiry, acknowledgement. Bell is interesting. If you open a Windows terminal on your PC, type echo space Control G and press enter, it'll play tada.wav. So you get a little, that's it, trying to ring the bell. We get onto the tabulation characters. Now, the thing about tab characters and vertical feeds and form feeds and carriage returns and all these things is these are control characters for a piece of mechanical equipment. Teleprinter had a thing called a carriage, and you print fine effect. Ooh, that's a very loud projector. And then when you got to the end of the line, what you would do is you would return the carriage so you could print another line. And then you would feed the line to the next one. Now, teleprinters couldn't do fonts. They couldn't do italic. They couldn't do very much at all. One of the things they could is they could do bold, because you could print the same line twice. Now, to do that, you'd do a carriage return, but then you wouldn't do a line feed. So a carriage return on its own was useful, because that's how you did bold. Line feed on its own, nah, not so much. You'd fall off the end, and then you'd need to go and put the pieces back together. And so we ended up with this interesting situation. Now, however many years later, we've got Linux and Mac OS going, yeah, /n, that's a line feed. And we got Windows going, no, no, line feed is /r/n. And it's not because Windows runs on mechanical teleprinters. It's all to do with backwards compatibility. You see, Mac OS and Linux evolved from Unix, and Unix evolved from a system called Multics. And Multics was the first system in history that had device drivers. It's the first one where you could put a little piece of code between your operating system and your teleprinter that could do useful things. Like if you get a carriage return, you probably want to put, or you get a new line, you probably want a carriage return as well. So just put one of those in so you didn't need to keep it in the text file. Windows 11 from Windows 10, from Windows 8, from Windows 7, from Windows all the way back to MS-DOS, which evolved from CP/M, which was designed to run on really, really cheap hardware so they could sell lots of it. And the cheap hardware did not have device drivers. And so if you wanted a carriage return a new line, you had to put both of them in the text file you're running. Now, the next chunk of ASCII, we get onto the alphanumerics. And there are some really interesting decisions being made in here. One, they had to decide what punctuation are we going to support. You've seen the thing recently, how M- has become like this signifier of someone using ChatGPT, and the people who actually write prose properly, like who worked in publishing, are like, no, we do that. Like, that's how we write properly. And they're like, no, we don't believe you. We think AI generated this angry email. Well, M- didn't make the cut, because they're like, look, we've got a minus sign, and it's a hyphen, and it's a dash, and you're just going to have to double up. We don't have space for all these kinds of things. The decimal numbers, one of the things computers have to do a lot is to turn numbers that make sense to a machine, which are binary, into numbers that make sense to humans, which are decimal. And so to do that, you just ignore the big half. And that gives you the binary value of that digit, 0, 1, 2, 3, 4, which is really fast, even on a 4-bit computer from 1965. Now, if you've ever looked at ASCII and been like, all right, well, a capital A is 65 and a lowercase a is 97, and you thought, why did they choose those values for capital and uppercase? It's because they differ by 1 bit. If you want to do case-insensitive searching or sorting, all you got to do is you ignore that bit. And then they're the same, and then it doesn't matter if it's uppercase or lowercase, you can still find it. They mop up a little kind of extra block of punctuation. We've got the opening brace, vertical brace, and then right at the end, you've got ASCII delete. And the ASCII delete character is all the ones. And the reason it's all the ones is there's only 2 ways to erase data from a paper tape. One is you've got to set it on fire, and they don't like you making fire in the labs. The other way is you've got to punch out all the rest of the holes so you can't see which holes were there in the first place. So the ASCII delete character would just punch every hole out of a piece of tape so you could no longer see what was on it. So you write deletes on the tape and then the data is gone. You've erased it. And so the Americans are like, hey, good job, everybody. 127 characters all you're ever going to need. And the rest of the world goes, come on. Now, this is where it gets interesting to me, because the first time I ever became aware of these problems, I grew up in Zimbabwe, and I grew up speaking English, and the Zimbabwean currency when I was a kid was dollars and cents. So ASCII solved every problem I had when I first started playing around with computers. Then when I was 10 years old, I moved to the UK. And I was doing some homework on my 286 PC with my Epson dot matrix printer. I wanted to print the pound sign in my homework. and I could not get it to print because all it would print was this. And the reason is, this is not one of the characters that made the cut. Pound sterling was not statistically probable enough in 1960s America to be part of the ASCII information interchange. Now, there are some places, in the United Kingdom, basically that's the only thing we were missing. They had everything else that we needed. Places around Northern Western Europe, Scandinavia, Germany, it's missing some of the accented characters they use, but you could kind of get away without them for a while. A lot of places around the world are like this, no. We can't even get started with this. This looks nothing like the way we read and write. And so a lot of people looked at ASCII and they went, well, hang on, there's 8 bits in a byte, which means we've got 256 characters, and ASCII only defines 128 of them. Is anybody using this bit? And of course, there was no standardization. And so everybody jumped in and went, brilliant, we're going to use the top half of ASCII and we're going to solve all of the problems. Now, the solutions are what are known as code pages. Code page is a rule that says, here, today, this program reading this document on this computer, this is what the top half of ASCII means. And the reason I couldn't print my homework is because the PC and the printer were using different code pages. So they couldn't even agree across a meter of parallel printer cable what code page something meant. This is where things get really gnarly. Now, the original IBM PC, early 1980s, it shipped with a default code page called code page 437. Now, the thing they did with this, they included the basic ASCII block, and then the top half of it, they included pretty much all the characters you need for Northern Western Europe, the places where they wanted to be able to sell IBM PCs because those countries had money. They included box drawing characters so you could do menus and little ASCII diagrams. And then they included half of the Greek alphabet. Because Greece was not a market they cared about supporting, but mathematics and physics was. So there's enough characters in here to write a high school maths textbook, but you can't actually write a letter to somebody in Greek. And then someone went, oh, hang on, the IBM PC isn't a teleprinter. Maybe we can reuse that first block and use it for things like playing card symbols and printers dingbats and stuff. Now, if you've ever seen an original PC crash really hard, what you get is a screen full of smiley faces and playing cards. Because all of the low-valued values that are in memory, the machine code instructions, they're just being interpreted using the default code page, and so you get this screen of smiling faces and gibberish. Now, there's a couple of wonderful stories from around the world about the way people tried to use code pages to solve their problems. There was an international standard for encoding the Cyrillic alphabet, which is used for Russian, Ukrainian, Bulgarian, and a couple of other languages around the world. But this one had a problem. And the problem was a lot of systems assumed that data would only be 7 bits. So if you took a Russian word like a privyet and you encoded that using the international standard, you get this sequence of bits. Now, WordStar, very famous word processor, that used the 8th bit as a flag to say, did we spell check that word already? And so that would get set on, set off randomly. A lot of networks would strip that. They'd use it for parity control. To this day, SMTP email is a 7-bit protocol. So when you send someone an email, it's being turned into 7-bit data, so it'll make it to the other end without getting messed up, and then rehydrated at the other end. So you lose your top bit from a piece of international standard Cyrillic, and what comes out the other end is unreadable gibberish. And so a bunch of smart folks in the Soviet Union said, we got an idea. And they created KOI8, the Kodevnama Informacija 8 bits. And what they did, they said, forget alphabetical order. We're going to create an encoding based on, so we'll take privyet, we'll turn it into that, we'll lose the top bit, and we'll design it so that the ASCII letters which are left kind of sound like the thing you were trying to say in the first place. And they flipped upper and lower case on purpose, so it was obvious that this thing had been garbled in transmission. But it meant you could send email in Russian, it would get garbled in transmission, it'd come through, but the person on the other end could still have a reasonable stab at working out what you were trying to tell them. Now, I did this talk in Nottingham a few years ago. Somebody comes up to me afterwards, they said, do you know about the Harry Potter book? And I was like, no. And they got their phone out and they sent me a link to this wonderful story on Reddit. About 2002, there's a Harry Potter fan forum on the internet, and one of the books has just come out. And the book is available in France and Western Europe, but it's not available in Russia yet. And so there's this conversation between a lady called Svetlana, whose name is in the record, and Claudette, who I've made up because we don't know what her name was. And they're emailing backwards and forwards. And I'm guessing at some point Claudette says, hey, do you want me to send you the new Harry Potter book? And Sveta says, yes, that'd be amazing. We cannot get new Harry Potter book here in Russia yet. Here's my address. It is in Russian alphabet. Please copy it carefully. And puts in Cyrillic a street address of an apartment building in Moscow. Send, click. Windows 2000, Outlook 2000, in French, it's what comes out. But, you know, Claudette I guess that's how they write addresses in Russia. Now, this is the same data. Nothing has got lost here because the underlying numeric value of those characters is identical. It's just being interpreted using a different encoding system. And so she copies that onto this envelope and posts it. And somebody in the Russian postal system goes, I know what the problem is. And they correct it. And it gets delivered. And this photograph ends up on Reddit attached to the whole story. Now, I used to go to Ukraine and Russia and Belarus and do conferences there a lot. And a lot of the kind of these little stories come from chatting to people who, they have the same problems we have. They have JavaScript and microservices, but they grew up with a different culture and a different alphabet. And that's where the really fun stories come from. And one of them told me to, what I want you to do, get your phone out your pocket, and I want you to go into whatever app, come on, you do the thing. I want you to go into the app that you use to listen to music, Spotify, Tidal, Google Play, whatever. I want you to search for that. You found anything? What we got? Billy Joel. Billy Joel, 1987. Billy Joel and his band become one of the first Western artists to perform in the Soviet Union. And they did a concert in Leningrad, the city which is now St. Petersburg, and it was recorded. And the recording was released, and it was called Concert, because that's how you write the word concert in Russian. And then at some point, somebody is putting this into a database. And this is some American record label is like, all right, and they're looking at their keyboard and they're looking at the record and they're like, K-O-H-U-E-P. It doesn't matter because that's just an internal database, right? Like the database is just for the record company. It's never gonna end up in public until streaming comes along. And Apple and iTunes and Spotify go to all the record companies like, do you just like have a big database of all your music? And like, Bob, give them the database. And Live in Leningrad is now immortalized as the title of that album, even though it is a nonsense word that doesn't mean anything. And my final story about weird things that happen with the Cyrillic alphabet is, do any of you folks read Russian? Okay, good. Because does that say anything? Because this, if you type this on a Cyrillic keyboard layout, this is the pattern that your fingers make. And if you type that same pattern on international, like a QWERTY keyboard layout, it says Taylor Swift. And Google knows this, because if you forget to switch from Cyrillic back to British keyboard layout and you search for Taylor Swift, Google knows what you were looking for. And this, to me, this is the hallmark of like being really, really famous, is if you can type the name of your band or your movie or whatever in Russian into Google with the wrong alphabet, and it's like, oh no, we know what that one is. That's famous, and it'll actually find it for you. Now, code pages kind of worked a little bit for a while until it got unmanageable very, very quickly because there was no convention. Like I already said, I had a computer and a printer that couldn't agree on how to print British. And if you wanted to like write a document in Bulgarian, were you going to use IBM Bulgarian or Windows Bulgarian or PostScript Bulgarian or Apple Bulgarian? Because they all had different Bulgarians. This is the footnotes of the Wikipedia page on code pages. And it was obvious once we'd invented, you know, the web was going mainstream, email was becoming a thing, all of these things were taking off, and we needed a better way of being able to communicate and send text backwards and forwards. And so the Unicode Consortium was established. And they set up, the project was started in 1988. They officially kind of ratified as a legal entity in 91. And their mission is to provide a single consistent way to represent each letter and symbol needed for all human languages across all computers and devices. That is a brilliant mission statement. Let's work it backwards. All computers and devices. Every single one of you in here, your smartphone, your laptop, your smartwatch, they're all using Unicode. And none of them had to pay for it, and none of them had to reinvent it, because it is a great standard. It is open, it is free as in speech, it is free as in beer. You can get the specs, you can implement it, you don't have to pay royalties. Anybody who wants to do text can use Unicode for free, because it's just so much better for everyone if you do. Human languages. Not just the languages that people read and write and speak today. There are people out there doing archaeological research. There are people translating Egyptian hieroglyphics they want to be able to put their research in emails as well. So Egyptian hieroglyphs are in Unicode. Ancient Sumerian is in Unicode. And that leaves a single consistent way to represent each letter and symbol. So what we've got to do now is we've got to figure out what a letter is, and then we'll be fine. Now, my favorite way of doing this is to go into a toy store and find a Scrabble set, because that's the ultimate, to me, the ultimate arbiter of what is and is not a letter. And this has generally worked out pretty well until earlier this year. I was in Hungary, and I was in Budapest, and I was giving this talk, and I was like, I wonder how Hungarian Scrabble does this. Now, they have a 7-letter word here, nunchak, and I went into a Hungarian toy store, and I bought a copy of Hungarian language Scrabble, and I was like, right, let's find, so I found this word nemchak. Nemchak sha tishik hanem whiskey tish. It means he does not drink beer, he also drinks whiskey. And you play that word in Hungarian Scrabble, and your opponent is going to go, no, that's not a 7-letter word in Hungarian, that's a 6-letter word in Hungarian Scrabble. And as an English Scrabble player, I'm looking at that tile and getting very, very uncomfortable. The Hungarian alphabet is wonderful. It has 44 letters in it. It used to have 43 letters, and then in 1983 they added another one. When I say they, this is the Hungarian Council on Orthography, because one of the things about who gets to decide? Like, who is if somebody wants to say there's that many letters in your alphabet, are you going to argue with them? Because they're like the official Hungarian government office in charge of this, and we're not. So I guess what they say goes, and the rest of us have to try and figure out how to make it work. This is the Hungarian alphabet. Now, these here, these are the same letters that we have in 7-bit ASCII. It has the same set of 26 letters that the Americans encoded in the 1960s. Then these ones, they have their own code point in Unicode. Unicode says, yep, that's a letter, we'll give it a thing, and if you push that key on your keyboard or you type that alt code, you're going to get that letter come out of it. Now, there's a couple of interesting ones here. Unicode has a letter Z, DZ, except it's one letter. That letter is in the Hungarian alphabet, but they don't use it. And the reason they don't use it is because it's not there for them. It's them for the Romanization of Macedonian. Because Macedonia has Latin and it has Cyrillic, and you've got to be able to round trip between the two without losing anything. So they needed a single code point that is a Z that goes to a Cyrillic Z and back to a Latin Z again. And so that one there kind of doesn't really get used. Now, if you look at a Hungarian keyboard layout, that's got its own idea about which things are letters, because as far as they're concerned, well, if it's got a key, it's a letter, and if it doesn't, then it's 2 letters, because you make it by typing 2 keys. So these are the digraphs. There is a letter trigraph, this one here, J. The word jungle in Hungarian is spelt with 1 letter, which is actually 3 symbols. And so we end up with this system. Now, finally, Q, W, X, and Y, those don't appear in the Hungarian language. They are only used for foreign names and foreign companies. And so if we break the thing down onto a Venn diagram, we got 44 letters in the alphabet. 35 of them appear on a computer keyboard. We got 38 of them in the Scrabble set, which doesn't include Q, Y, X, and Z. Unicode recognizes 36 of them. This one comes off over here because it's there, but it doesn't get used like that in Hungarian. Now, when I did this talk in Budapest, I got to this point, I said to the audience, how many of you does this make perfect sense? And about 3/4 of the audience who are Hungarian are like, yeah, it's fine. And the others who are visiting for the conference are looking at each other like, are they serious? Like, because if, you grew up with English or American English or Australian English or Canadian English, we got 26 letters and 26 keys and 26 Scrabble tiles, and we've never really thought about the fact that this might be an open question for somebody out there. Let's meet some friends of mine. Francois Board is the archaeologist from France, and Motley Crue, the rock band from Los Angeles, California. Now, this sentence is in English. Francois the archaeologist went to the Motley Crue concert. It includes letters which are not part of the Latin, the English alphabet that we use here. Francois the archaeologist, well, Francois has a Cédille in his name, which is a French C with a little tail on it, and we recognize that because Francois says, I'm Francois, like this, and we go, all right, we can respect that. The archaeologist there, that is a thing called a typographer's ligature. It is an affectation. Some magazines and publications, they still use that because they think it looks cool. And Motley Crue, they have the heavy metal umlaut, which they picked because they thought it made them look cool. And then they went on tour in Germany, and the audience is chanting, Mötley Crue. I'm like, why can't they get our name right, dude? And it's like, that's a letter here. Do you know that? Now, These characters, they're not part of the English alphabet, but we use them anyway. We use them in English prose, and it goes both ways. If you've ever been to Poland, and you have been on your way to the city of Łódź, and you've been searching for it on your phone so you can buy a train ticket, we don't have these letters on our English keyboards or in our English-speaking brains, and so we just kind of ignore the extra bits and we filter those out, and so instead we try to buy a train ticket to Lodz. And Google Maps is like, well, yeah, obviously you mean Łódź because you're looking for Lodz. So these are the kind of decisions that people have to make when they're implementing software that has to work internationally, has to work across boundaries. People who don't even have the right keys on their keyboard still want to be able to buy a train ticket. So you need to figure out what it was you thought they were asking for. Let's meet Magnus. Magnus Mårtensson he's a Swedish Microsoft Azure MVP. And he has a lovely story. A couple of years ago, Magnus is on his way to Seattle for a Microsoft event. And Magnus has a Swedish passport. And if you look at a passport, you've got 2 rows at the bottom here, 2 or 3, which have to be machine-readable ASCII, because that's the rules, because the international system that manages airline reservations, there's 2. There's one called Sable, one called Amadeus. They run on IBM mainframes. They're written in COBOL. So they have to be American machine-readable 1965 ASCII. Now, the rules of Swedish orthography say that if you have the letter O, which is A with a little circle on it, and you have to turn it into ASCII, it's AA. You use 2 A's on that. The people who print Magnus airline ticket, they just take the circle off because they're not Swedish. They don't care about the rules. And so Magnus ends up with a passport that doesn't match the name that's on his airline ticket. To get into the United States, who are famously relaxed and forgiving when it comes to people not having the correct papers. Now, he's a well-dressed white guy on his way to a Microsoft concert. You think about the number of people around the world every day who are trying to get across a border, and they got a passport that has mangled their name in one direction to fit in ASCII, and they got a plane ticket or a train ticket or a driving license that has mangled their name a different way. I have a passport at home with 3 Russian visas in the same passport, and they spelt my name in Russian wrong 3 different ways in the same passport. Because every time it came back, they mangled Beattie into something different in Cyrillic. You imagine the kind of people who they're just like, nope, you know what, we're not letting you in. This is just because ASCII. This is just because text encoding. Let's talk about alphabetical order. We're going to take a list of European cities. We got Berlin, we got Aachen, we got Zurich, we got Aarhus, and we have Örebro. And we are going to put them in alphabetical order. Show of hands, who thinks number 1 is in alphabetical order? Who thinks number 2 is in alphabetical order? Who thinks number 3 is in alphabetical order? And number 4. You're sitting there going, what do you mean? How can alphabetical order be different? What kind of question is this? They are all in alphabetical order for somebody, somewhere on this planet, because alphabet is not a fixed concept. It varies. People change their mind about it. We're going to put them in a database. So we're going to open up SQL Server, and we're going to create a table called cities. We're going to insert Berlin, Aachen, Zurich, Aarhus, Örebro. Let's do a quick select star from cities. There we go. Let's select star when name equals Örebro. Nothing. All right. Maybe it's case sensitive. Nope, still nothing. Okay, let's see. Is Örebro the same as Örebro? And it's going to say, no, they are not, because they're not. Unless we say, please tell me, are these strings the same according to the Latin 1 general case-insensitive, accent-insensitive collation? Set of rules for saying, are these letters the same? And if they're not the same, which one comes first? According to those rules, yes, the strings are the same. Now, this is where it gets interesting. If we select star from cities order by name, we get Aachen, Aarhus, Berlin, Örebro, and Zurich. This makes sense to me as a British speaker because to me, is not a letter of my alphabet. It's an O with decorations, and the decorations don't matter. That's not true, though. At least it's not true in other places. If we specify the collation, this is the default, it's the one that makes sense to English speakers around the world based on the Latin alphabet. If we use the Finnish and Swedish collation, now moves to the end because is the 29th letter of the Swedish alphabet. Because Swedish goes from A to Z, and then it has O, E, and on the end of it, and so is the 29th, so that one appears after Zurich. Now we do it with Danish and Norwegian collation. And now Aachen and Aarhus move to the end. And this does not make any sense whatsoever unless you grew up there, and even if you did, this is still wrong. The reason is Aarhus is Denmark's second city, the second biggest city there after Copenhagen. And the city of Aarhus was officially spelled Aarhus with the little A with the circle on it from 1948 till January 2011. 1948, there was a thing called the Danish spelling reform. They, following World War II, and you can probably guess why, Denmark wanted to be more Swedish and less German. And one of the things they did was they reformed their alphabet. They borrowed 3 extra letters, which are similar to the ones used in Swedish. And they said, right, this sound or, which appears in a lot of Danish place names and people and companies and those kinds of things, we're going to replace that with the new letter or, which is part of our alphabet. Then in 2011, they voted to change it back to Aarhus because they thought it was interfering with their Google foo for tourism. You know, who gets to decide? I guess the people of Aarhus get to decide. Thing is, that doesn't change its position in the alphabet, because or is still the letter or, it's just being spelled differently. So Aachen goes at the beginning. Aachen is in Germany. It's not in Scandinavia. So AA in German belongs at the beginning of the alphabet. AA in Danish and Norwegian belongs at the end of the alphabet. To people in Denmark and Norway, this makes perfect sense and there is nothing weird about it at all. To the rest of us, we're like, how? And you can't get it right. That's the problem, is the database does not know that Aachen is in Germany and Aarhus is in Denmark. So if you actually have this as a requirement for your customers, the only way to solve it is you've got to put another name in your database that says, look, if you're doing alphabetical order for somebody in Scandinavia, then you need to use this extra column to override the sort ordering, and then you get back the cities with Aachen, Athens, Berlin, Zurich, Örebro, Aarhus in the correct order. Now, once in a while, you get people pop up and go, oh, you know, I don't want to bring politics into it. I just want to write code and solve problems. And you can't even get alphabetical order right without understanding the geopolitics of Europe in World War II and beyond, the Danish spelling reform, orthography, place names being in Germany or Scandinavia. Politics creates problems and technology has to solve them. And so if you don't understand the politics, you are going to spend a great deal of your career just bashing your head against the wall, wondering why everything is stupid and nothing makes any sense. On the subject of which, let's talk about capitalization. Because at the very least, we agree that whatever country, alphabet, language, writing system you're using, if you have 2 uppercase, that's always going to take the same lowercase letter and give you back the same uppercase letter, right? Well, that sounds like a pretty reasonable thing we can agree on around the world. No. Turkish has a capital and a lowercase I with a dot, and a capital and a lowercase I without a dot. And I had a plane ticket to Istanbul a while ago, which I never got to use because of geopolitics. But if you look very closely, Istanbul is spelt with a capital I with a dot on the top of it, because this is how Turkish orthography works. Now, the problem here is you think about them trying to take this alphabet language writing system that they've used for decades and turn this into something that works with digital computer systems. The problem they've got is we already have, these are the extra letters, but we already have the others. So one scenario says, all right, well, if you have a lowercase I with a dot and you capitalize it, it becomes the uppercase I with a dot. Now, this means you've gone from 7-bit American ASCII straight into an extended Unicode block just by uppercasing something. But the alternative is that you'd have to have 2 keys on a Turkish keyboard, which were both a lowercase I, because one of them's the Turkish one and the other one's the other one, which also doesn't work. And the same problem in reverse. When you take an uppercase I and you lowercase it, it doesn't get a dot if you're running code with a Turkish locale. Wikipedia just says about it, has caused some issues in computing, is what it very diplomatically says about this. Now, let's go back to our friend Francois and the C with the cedilla on it. What Unicode says about this is like, look, all right, we'll give you, if you want to C with a cedilla, yeah, we'll give you a code for that. If you want that, or you got a key on your keyboard or your device that does that, you can do that as a single letter. But maybe you don't want to do that, because in English, we draw an English C and then we put a little decoration on it. And so Unicode says, right, well, we'll give you decorations. You can draw C, and then you can put a Unicode plus 0327. Now, that's what's called a combining character. And a combining character is basically garnish for the thing that you just drew. And the lovely thing about these is you can stack them, because you can say, I want a Z with one of those, and one of those, and one of those, and one of those, put that on top and that underneath. And if you stack these enough, this is how you get Zalgo text. And this one is a great way if you're building your own font renderer. It's a wonderful way of testing it. You could send someone a text message to their Samsung Galaxy phone that would brick it and it would never boot again. because it would just cause this overflow problem with the text rendering in there. But what this means now is that even if we've agreed which letter of which alphabet, in which case, in which culture we're drawing, we got more than one way to draw the thing, because we could write Motley Crue as Motley Crue, or we could write it as M and then an O and then a combining diaresis and then a TLE. So we got two different, now they look the same, they sound the same, they read the same, they mean the same thing, but they're not actually the same string. And this is where Unicode goes, right, well, we're not going to tell you how to fix this. We're going to give you tools. We're going to give you normalization forms. So canonical decomposition means letters are fixed. Just because they look the same doesn't mean they're the same letter. And I want you to decompose them by breaking them out into the widest possible sequence of code points before you compare them. Composition does the opposite. Squash this down as small as you can. Compatible, at this point, they're like, we used C already, damn. All right, compatible in Unicode spelled with a K. Everyone fine with that? Right, come on, let's go. And compatible composition is the opposite. Now, what this means in practice is if we build a string, so we've got the string Motley Crue there that we've built out of an array of chars, but then the next one, we're building Motley Crue by adding a combining diaresis using a Unicode escape. And so we've got two strings, S1, S2, and if we run the code that compares them, they're the same length. Now, they're not the same length because we've put a different number of chars into the array, but .NET is smart enough to know, no, combining characters don't make things longer. They don't increase the number of characters. So one of the questions, you want the length of a string, you're like, well, how many letters or how many bytes? You need to think about this stuff. And it's saying, well, they're not equivalent, but all four forms of Unicode normalization say that they're the same string. So if someone searches for Motley Crue, it doesn't matter which way around they typed it, you'll still find it. Now, if we take plain text in decorative bubble writing and compare that to plain text, now it says, well, okay, run the code again, and it says, okay, same length, they're not the same data, and the canonical composition says they are, canonical normalization says they're not the same. But if we use the compatible form, it's like, well, yeah, they both say plain text. So if you want to search like a username database and you've got one of those systems where people can use fancy Unicode writing in their usernames, you're going to need to use a compatible composition to be able to find them when you're digging through your own data. Now, second big turning point in my sort of personal journey with the wonderful world of text encoding came about 10 years ago. I went into work one morning and one of my team says to me, dude, I think we've been hacked. Now, this happens a lot when you work in tech because people are always breaking their computers and they always think it's hackers that did it and not them clicking the wrong thing or downloading the wrong thing or going on Pirate Bay. But the person in question was a security engineer on my team, was actually very, very good at his job. And I said, why do you think we've been hacked? There's Chinese in the Windows event logs. And there was. I actually took this screenshot that day and then found it on the blog post when I put the talk together a couple of years later. There is Chinese in the Windows event logs. Now, incident management 101. Okay, this might be very, very bad. Okay, your job. I want you to go and tell the business we might have a security breach or a database problem. We'll get an update for you in 15 minutes. In the meantime, if anyone hears anything weird or you get weird calls, please put them through to us. You check the firewall logs. Any intro, like, do we get a massive spike in traffic from Beijing in the middle of the night or something? You check the database. Is it an injection attack? Is there Chinese data in any of our tables anywhere? I have now delegated all of the important parts of incident management, so I get to shitpost about it on social media. And I won. I solved the problem. Because, well, Twitter solved the problem back when it was good, because I immediately got a friend of mine go, that looks like a Unicode mapping error. UTF-8 being treated, and then fake Unicode pops up and says, the low bits are all null, so this is probably UTF-16LE being mistaken for UTF-16BE. I'm looking at this and I'm like, that sounds like it might be really important. I should probably find out what that is. And so I did a very, very rapid crash course in what is UTF-16 and why does it come in LE and BE. And what I learned that morning is internally, Windows, Java, .NET, JavaScript, quite a lot of like operating systems and programming languages, they use a thing called UTF-16, which means that every character is stored as 2 bytes. And the reason they do this is because it's predictable. It means you know if you've got a bunch of text, you know how much memory to allocate for it. You know roughly how far to jump when you're doing things like a binary search, because you can mostly rely on all of the letters, all of the glyphs of data being the same length as each other in memory. And so the word delete in UTF-16, now LE and BE are which one comes first, little end or big end? Little end first, big end first. Because if you take the word delete in 16-bit UTF-16, and you flip it into the wrong encoding, it teleports you straight into the middle of the Unicode block, which is used for Chinese. Now, this talk, I remember on the day that this happened, someone ran the translation through Google Translate to see if it was some kind of, like, it made any sense or anything. And I remember them coming over to me and saying, now, a couple of years later, this got posted on the YouTube video. And this guy, I mean, like Nicholas Chan, I kind of assuming from his name that he speaks Chinese, but maybe he's just in San Francisco and he has Google Translate. I don't know. But he said, this is what it means. That one is dismembering the body of a livestock. That one's climbing. That one's textiles and fabrics. This one is gems and pearls and jade put into the mouth of a corpse. Now, I laughed my ass off when I saw this because it reminded me the day that it happened, the person who Google translated it came to my desk and said, I think it might be a ransom note. And I'm like, what do you mean? I think they want us to put a diamond in a chicken or something. And I'm like, no, I do not think that is what we are going to do here. So next question. Why is our Microsoft Dynamics CRM database server flipping from UTF-16 LE to BE and back again? Now, what was happening is it would go down for about 2 or 3 minutes. And then we would try something and it would come back. And we'd be like, all right, it's back, it's back. And then 2 or 3 minutes later, it would go down again. And then it would come back again, and then it would go down again. And it did this for something like 30 hours. So we're kind of on, did we fix it? No. Oh, it's broken again. Oh. Did we fix it? It's back again. Did you do anything? Nobody did anything. What we eventually worked out, there was a faulty network switch. We just moved everything into a new virtual hosted data center. And there was a virtual network switch in there that was dropping one packet roughly every 3 minutes. Just one little packet disappearing, 1 byte. And so everything else then just got shifted sideways without any indication this had happened. And UTF-16 just keeps on trucking because it's like, oh, yeah, Chinese, all right. We can do this. That's fine. So very, very good for local storage. It's good for memory. It's good for operating systems, programming language design. One, it has this problem. If you lose a byte in transmission, you have no idea that it happened. You've just suddenly gone into the middle of a different Unicode block and back again because all of these are valid encodings. The other problem with it is let's imagine that we want to write a web page which just says hi in Ukrainian. And this is what that is going to look like in UTF-16. Now, even if our web page is in Ukrainian, Arabic, Korean, Hebrew, HTML is built on ASCII. CSS is built on ASCII. JavaScript is built on ASCII. And an awful lot of most modern web apps and stuff, this is the bit of this web page that actually needs the extended characters. The rest of it is just us going null 3C, null 21, null 44, null 4F, null. Which means 44% of the data that we are sending through these undersea cables and around the world is redundant. We are just sending null over and over and over again. It is a very, very inefficient format when you go from local memory to actually sending stuff across a network. And so the Unicode Consortium came up with what I think is probably the cleverest hack in the history of doing smart things with computers. They said, right, it's UTF-8. Any byte starts with a 0, that's American ASCII, same as it's been since 1965. Every single document on FTP and Usenet and floating around the web that's in plain text, those are all UTF-8 now without having to change a single byte, which is genius. Then they said, right, if you're looking at a byte that starts with a 1, that's part of a multi-byte sequence. Look at the next byte. If the next byte is a 0, you are halfway through a letter. You need to backtrack. If the next byte is a 1, then 110 means this is the beginning of a 2-1, so it's a 2-byte sequence. If you've got a 1110, this is the start of a 3-byte sequence. If you've got a 11110, this is the start of a 4-byte sequence. And then the red X's here, those are the bits you then decode to give you the actual value of the character. Now, in theory, this goes all the way up to 1111, like you go all the way up to 8. We don't need to do that because that is way more headroom. Like even if we make contact with the aliens from Alpha Centauri and all of their archaeologists want to be able to put their stuff in Unicode, we've got enough space to do that. But we've also got enough space to invent new alphabets, which is kind of neat because we like inventing new alphabets because there's an alphabet that's been invented in my lifetime that I'm sure all of us have used today. And I know ChatGPT loves to use this alphabet. It's the alphabet called emoji. And this is the original emoji character set. It was invented in 1998 the Japanese mobile phone company Docomo, they had a project called iMode, which was like an early precursor to mobile smartphones, which was being able to get, traffic transport timetables and fast food and things on your phone. And they hired an artist called Shigetaka Kurita to come up with this little set of icons. This is now in the Museum of Modern Art in New York, the original set, as a sort of testament to how influential this has been. Then this takes off in Japan in a big way. Like within 2 years, you can't sell a phone in Japan that doesn't have emoji because no one wants a lame loser's phone that can't do emoji, which means when Apple launches iPhone in Japan, it's got to do emoji, otherwise no one's going to buy it. Which means the rest of the world then goes, hey, if you go into region settings and set it to Japan, you get all these little cartoons that you can send people in text messages. Which means people start asking questions like, well, there's sushi here, but there's no tacos. I want to go for tacos. Where's my favorite fast food? And people noticing, well, okay, there's an airline pilot and a firefighter and a police officer, but they're all men. This is not really fair. And then there's a whole thing about skin tone representation going on in here. Now, there's only a handful of times in history that Apple and Google have got their heads together and collaborated. Emoji was not a standard at this point. It was basically a kind of loose affiliation of handset manufacturers playing catch up with each other. Apple and Google turned to Unicode and they're like, look, if we do the engineering to get this thing up to kind of parity and hand it over to you, will the Unicode consortium steward it from now on? They said yes. And so they did. By about 2015, this was completely a Unicode standard. And one of the first things they did was they introduced the ability to use skin tone modifiers on emojis, faces and hands and those kinds of things. And they did it using combining characters, the same way as Francois. They said, all right, well, we'll introduce a new Unicode combining character. Now, the idea here is that if your mobile device has the artwork and it sees this character sequence, it will render the custom artwork for that skin tone. If it doesn't, you get a thumbs up followed by a little one of those squares that says, we don't know what character this is. And you know it's time to install an update or go and get a new phone. And they've come up with all kinds of brilliant ways of using things which have always been part of the Unicode standard to support all sorts of interesting representation artwork. So there's a female astronaut emoji, which is a woman followed by a thing called a zwidge, a zero-width joiner, which has been in Unicode originally to support an old Irish kind of Paleolithic writing system. But then they went, hey, we can use that one. So a woman plus a rocket, zero-width joiner. If your handset doesn't support it, you get a woman next to a rocket and you can figure it out. And if it does, then you get a female astronaut. And you can combine that with the skin tone modifier. And so you get these different combinations of, identity and ethnicity and occupation and family configuration. Now, flags is where it gets really interesting. The flag of the United Kingdom is a country, according to the International Standards Organization. We've got an ISO country code. We've got GB. And so the regional indicator symbol GB, that gives you the flag of the United Kingdom. Same for all of the countries which are recognized as countries by ISO. England's not a country. I mean, it is for football and rugby purposes, but not for the Olympics or Formula One, and not for ISO. So the England flag does not have an ISO character designation. And so the Unicode folks are like, well, we probably better have that one because there's a lot of money in football. So they said, what about if we use the black flag followed by the tag Latin small letters GBENG for Great Britain, England. Same thing for Scotland, same thing for Wales, and the same thing for the flag of Texas, because those are currently the only 4 regions that have flags in Unicode which aren't actually countries. And then the pride flag is a white flag, a zero-width joiner, and a rainbow, which I think is rather lovely. Does anyone recognize this flag? Taiwan. Well, technically the Republic of China, the country everyone knows as Taiwan, not to be confused with the People's Republic of China, which is the country everyone knows as China. Now, the problem with that flag is there's about 1 billion people in China, the People's Republic of China. They have money. They want to buy iPhones. Apple wants their money. This flag in mainland China is a symbol of Taiwanese independence, and that is not the done thing. The government does not like that at all. So if you go into your iPhone and you go, Taiwan, look, there's the flag, and then you go into your regional settings and change your phone's location to China mainland, when you go back into your little text message you were writing, it's vanished. You can't see it. Now, the nuance I think is really weird here is you cannot see or type the flag of Taiwan. You can see the flag of Hong Kong, but you can't type it. So you're allowed to read only Hong Kong, but you don't have read write Hong Kong. Taiwan is completely off limits. All of the others are there. This is the deal that Apple made with the Chinese government to be allowed to sell iPhone in China. They said, all right, if anyone's in China, then we will switch off the Taiwanese flag and you can all get on with pretending that doesn't exist because the rest of the world knows that isn't true. But of course, there's no politics in technology. Microsoft, when we're not touching that, no, we're not going anywhere near it. If you have a bunch of flag emoji and a text file on macOS and then you open that same file on Windows, it just goes, no. All we're going to do is give you the regional symbol indicator letters so you know which country it is, but you can't see the flags. There's only 3 flags that are actually supported on the Microsoft Windows operating system. They are the pride flag, the skull and crossbones, and the checkered flag that means you just won the Formula One. Now, I think this means Microsoft's official position statement on flag emoji is that gay pirates are winning, but I don't know, don't quote me on that. And then the final kind of chapter, the thing which inspired me to take all this and mash it together and turn it into some kind of presentation. I was in Ukraine in 2016, 2017. I was at a conference there, and it's my first time visiting any country which used the Cyrillic alphabet. And I could not read or write anything. And I'm walking around like, oh, yeah, I don't know what that is. I don't know what that shop sells. I'll have one of those. I don't know what it is. Is that pasta? I'm not sure. And I had a great time there, really, really interesting place to visit. And I noticed, I turned to one of my the people who was hosting us out there, one of the locals, and I was like, why does Ukraine use the English alphabet on their car license plates? And he said, we don't. I'm like, yeah, you do. I can read all the car license plate. I can't read anything else. Now, this sent me down a rabbit hole. And it turns out, 1965, the same year that ASCII was first formalized, there's a thing called the Vienna Convention on Road Traffic. And all the countries all over mainland Europe, they all signed this treaty that said, look, if we're going to drive cars over the borders so we can go on holidays and stuff, it'd probably be a good idea if we had a agreement on like maintenance standards and these kinds of things. And one of the things that that treaty said is that license plates have to be written in the Latin alphabet. And the Soviet Union signed the treaty despite the fact that their license plates look like this. Now, I'm guessing there was a meeting where somebody said, comrade, what if you want to drive car out of Soviet Union? And someone said, comrade, you do not drive car out of Soviet Union. Because if you did, if you could get the travel papers and the permits and everything, because, the USSR was closed, you could just go on holiday. You had to get government party approval for it. They'd give you temporary license plates at the border that you had to bring back, otherwise bad things were going to happen. The local license plates looked like this. Now, in the 90s, when the Soviet Union collapsed, all the various member states, one of the things they overhauled was vehicle registration. And today, Belarus, Ukraine, Russia, their license plates look like this. And what they did is, I think, another quite neat little hack. In Ukraine, what they did is they took the Cyrillic and the Latin alphabet and they identified the set of glyphs. So these are not the same letters, they are the same shapes that appear in both of those alphabets. And they said, that's it. That is the subset of letters that we are going to use on our vehicle registration system. And if you take that particular subset and you rearrange them a little bit, you get the English phrase PIKE MATCHBOX. Now, the reason I leave you with that is that next time somebody says to you, oh, I'm going to send you a plain text file, can you take a look? You say to them, do you know about PIKE MATCHBOX? And if they say yes, then they've seen this talk. It's like a little shibboleth. And they know about the Danish spelling reform and big endian and little endian and UTF-8 and the Taylor Swift encoding and Ukrainian license plates and all that kind of stuff. And so they're going to send you a text file that they've done the diligence on it and it's encoded properly. If they say to you, no, what's PIKE MATCHBOX, then they're going to send you a file that works on their machine. And it might work on your machine. I don't know. There's no such thing as plain text. And I always like to dedicate this talk to Joe, who watched the whole thing on YouTube and commented at the end, leave politics out of software. Thank you. Thank you very much, folks. We have, do we have questions? Or actually, what I love is, do we have weird stories about how that's not how they do it in the place where you grew up? And let me tell you this weird fact about our alphabet. Or do we have the silence of complete enlightenment, total understanding?